Welcome to the content material for Class 9 of Engineering Statics. You should be watching this video before your ninth class. In this lesson, we will describe how to find a moment about a specified axis and the moment from a force couple. Last class, we learned how to find the moment of a force about a point. For example, this is a wrench that is applying a force to a lug nut on a car wheel. We could find the moment caused by this force F about the point O. We could take the cross product of the vector from the hand to the lug nut and take the cross product with the vector force F. We would find the moment about the point O, which would look like this. However, the lug nut cannot rotate around this axis. It can only rotate around the y-axis. So what we really want to know is this moment about the y-axis. We want to know this moment my. The moment my is equal to the force F times the perpendicular distance to the y-axis dy. In this case, we want to find the moment of a force about a specified axis. We can do this by using scalar or vector analysis, just like when we found the moment about a point. In the scalar analysis, the magnitude of the moment about any axis, which we can call the a-axis, is equal to the magnitude of the force F times the perpendicular distance to that a-axis, dA. In general, the moment about any axis is equal to the magnitude of the force times the perpendicular distance to the a-axis, dA. In the vector analysis, we find the moment first, so r cross F. Then, we take the dot product of that using a unit vector that goes along the axis that we're using, the a-axis. So a unit vector along the axis A, UA, dot product with the moment, which we can find using the cross product. So in our example with the lug nut, the axis we're using is the y-axis. So the unit vector is just j hat. So the moment about the y-axis is found using the dot product of the y-axis unit vector, or j hat, with the moment. We can use the determinant to find the moment as well. If we place the unit vector components in the top, we're able to find the moment about the a-axis. And so the determinant would be calculated this way, using the determinant. Let's look at some examples. So in this example, we have three forces that are acting on this box. We have force 1, force 2, and force 3. And what we're asked to find is the resultant moment around each axis. So what we're looking for is the magnitude of the moment about the x-axis. We'll call that mx. So the way that we can do this is we'll just use the scalar approach. Now what we have to remember is that if a force passes through the axis, so for example if this is the x-axis, and a force passes through the axis, the moment is equal to 0. If a force is parallel to an axis, then again the moment is 0. So let's start with the x-axis. We know that we're looking for the resultant, so that we have to add up each force moment. Okay, so force 1 we're told is equal to 60 pounds. Okay, so what we see is that dx1, this distance here, is equal to 2 feet. Force 2, we're told, is equal to 50 pounds. And that distance is also equal to 2 feet. Force 3 is 0 because force 3 is parallel to the x-axis. So this one is parallel, so its moment is 0. So we see that for the moment about the x-axis, it's equal to 230 pound-feet. Now both of these are positive using the right-hand rule. So we start by looking at which way that the force would rotate around that axis. So both of these rotate in the positive direction using the right-hand rule. Let's look at My. In this case, force 1 is 0 because, again, it's parallel. Force 2 works in the negative direction and has a magnitude of 50 pounds. So if you hold your hand as if it's on the y-axis and you rotate with the right hand rule, it would have to rotate around like this in the positive direction. But we see that force 2 is going to cause it to rotate this way, and so that's why that one's negative. And the distance for dy2 is over here, right? So dy2 is over here, and that's equal to 3 feet. And we have another negative force over here for F3. F3 again rotates in the negative direction, so 40 pounds. And dy3 is here, is equal to 2 feet. So when we plug those values in, we see that it is negative 230 pound-feet. Last, we have the moment about the z-axis. So, force 1, force 2, and force 3. Force 1 is 0 because it goes through the z-axis. Okay, so this goes through the z-axis, so this one is 0. Force 2 is parallel to the z, so again this one is 0. Force 3 goes in the negative direction. Again, using the right-hand rule, we see that it's negative. Force 3 has a magnitude of 40 pounds, and dz3 is equal to 2 feet. So we find that mz is equal to negative 80 pound-feet. In this problem, we're asked to find the moment along the AB axis. So the moment created by the force F along this AB axis. And we know that the magnitude of the moment about the AB axis we can find using the dot product of the unit vector. So this is the unit vector along AB, and then the moment, which we can find by taking the cross product with the force. Now this R can be any R that goes from any point on AB to the force F. So if you look in the second picture there, there's RC, there's RD, And we could draw many different versions of these r's, and all of them are okay, because r can go from anywhere 1ab to anywhere 1 the force F. So we're going to choose RD. So we're going to choose RD. RD. So we need to know what that is. Well, RD is, we choose it because it's easy. It's simple. It only goes in the x direction. So RD is equal to 0.6 meters in the I direction. We also need to know F. F is equal to, it points downward in the Z direction. So now we just need to know U, A, B. Well, that's equal to the vector that, the position or the direction vector that goes from A to B divided by its magnitude. So let's find RAB. RAB goes from the x we can plug those values in. We have units of meters, and so we see that we have 0.4 I, 0.2 j, and no z. So that vector does not go vertically, doesn't go up or down. And we find the magnitude equal to the square root, 0.4 squared. And we see that's equal to 0.447 meters. Okay. The unit vector, therefore, is equal to so here's our unit vector. Now we have everything we need to do the dot product and the cross product. So we're going to set up our determinant. So we know that the magnitude of the moment about the axis AB is equal to the unit vector times the dot product of this cross product. And we're going to set up a determinant. The determinant, we put the unit vector x, y, z, our RD, and our force. And we plug in the values that we have. And we follow our determinant rules. So, first, start with our first column. And we see the answer is 0. 0 times 0. So 0 minus 0, because we have 0 here and a 0 there. And now we want to do the next, the y component. So here we remember to always put the minus first, and we start with 0.4472 times, and we make our x, 0.6 meters,
negative 300 newtons minus 0. And now finally we move on to the last component. We see that this value is equal to 0. So 0 minus 0. So when we plug these values in, we find that the magnitude of the moment AB is equal to 80.50 Newton meters. And last thing, if we want to put this into vector format, we show that we take that magnitude and we direct it along that unit vector in AB. So it's equal to that magnitude times the unit vector, 0.9. There we have it.
The next topic we will consider today is the moment generated from a couple. A couple is defined as two parallel forces that have the same magnitude but opposite directions and are separated by a perpendicular distance d. Since the two forces are equal and opposite, the resultant force is zero, but the couple will create a moment and cause a tendency to rotate. For example, consider this steering wheel. Pushing and pulling on the steering wheel with equal forces will mean that the wheel cannot move forward or backwards, but it will turn. The moment caused by a couple force is called a couple moment. And just like before, we can find a couple moment using scalar or vector analysis. For scalar, it is F times d, where d is the perpendicular distance between the two forces. For vectors, it is r cross F, where r is any vector that goes from one force line to the other. So it could be any of these vectors r. Because we can use any vector r that goes from one force to the other force, it lets us choose where we want to draw the vector r, and you can choose any point. And so let's look at an example of that.
In the last example, we're looking at a force couple, and this creates a couple moment. So these two forces are acting in equal and opposite directions. We have F and we have negative F. And we're asked to find the couple moment. So what is the moment? Well, we can do this two ways. We can do this using a scalar approach and a vector approach. Let's look at the scalar approach first. Remember, with a couple moment, we can break the forces into their components and choose any point. So what I'll do is I will choose this point, and I'll call it point A. I'll call this point B. So I will choose to do it about the point A, because that way I can ignore this force. Since it acts through the point A, that moment is equal to 0. And I only have to focus on this force down here. And so here we had the force in the y direction and the component in the x direction. And we'll call this positive according to the right-hand rule. So the moment about A is equal to positive Fx. So the x component causes positive rotation times the distance away, which is 2 meters, 0.2 meters. Same for this direction. Minus Fy, because Fy causes the rotation in the other direction, which is negative. So the moment about A is equal to 600 times cosine theta times that distance. So this is Fx minus sine theta. And here is Fy. When we plug those values in, we find that Ma is equal to 43.9 Newton meters, rotating in the counterclockwise positive direction. But we can also do this using vectors. With a couple force, we can draw any vector that goes from one force to another and take the cross product. So if I draw this vector r from B to A, r from B to A, I can find the moment is equal to the cross product. Now be sure that we choose this force as the F and not this one, because we want to choose the one that the vector points to. So RB points to this F. Okay, so we just need to define these values. RBA goes positive in the X, positive in the Y, and that force F goes negative in the X direction and negative in the Y direction. So now the moment is equal to the cross product of these, which we can do using the determinant. So this is RBA, this is F. Remember your negative signs. So here we have 0. So there's a 0 and a 0. Minus, also 0, plus, so we have k hat times 0.2 meters times negative 600 sine 30 minus negative 600 newtons and cosine. And so when we put those numbers in, we find that the moment is equal to the same value we got before, positive 43.9 Newton meters.
Finally, if two vectors produce a moment with the same magnitude and same direction, then these two couples are equivalent moments. For example, the two couples shown are equivalent here because each couple moment has a magnitude of 12 Newton meters. In this example, the force is 30 newtons and the perpendicular distance is 0.4. So the couple moment is 12 Newton meters. In this example, the force is larger, 40 newtons, but the perpendicular distance is shorter at 0.3, and again, the moment couple is 12 Newton meters. So these moments are equivalent. That's it for today. Be sure to check out the practice problems and get ready for the quiz.